When the working substance is placed on the source, the pressure decreases and volume increases in this case. Isothermal means the temperature in the system is kept constant. What is this PV? PV is nothing but nRT according to ideal gas equation. Why this is T2? T2 because during the third condition the T2 remains as it is, that is T1 changes to T2. Hello everyone, I am Brinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 3 of chapter 12, and chapter name is Thermodynamics. So in today's class, we are going to discuss about the Carnot Cycle, which is the last part of the Thermodynamics chapter, and it is very important in the exam point of view, which consists of 5 marks out from this question. So now let us begin with a session about the Carnot cycle. So Carnot cycle, it is a 4 steps of a reversible cycle. After those 4 steps, it gets reversed back again. So here we have representation of curve AB. So in this Carnot cycle, we are checking the working substance where exactly is kept upon. It's upon the source or the insulating stand or the sink. Okay, so first of all, the working substance is kept on the source. So what happens when the working substance is kept on the source? The curve whatever we obtain will be, we are drawing a PV diagram, pressure versus volume diagram. Okay, so first of all, here the temperature is set to be constant because the curve whatever is undergoing will always be with respect to a constant temperature. That means we can say when the working substance is placed on the source, the pressure decreases and volume increases in this case. Therefore, the isothermal expansion is taking place. So here the pressure decreases but the volume increases. So the volume is increasing, its height has decreased. So this is the way which shows the representation of the curve AB in the first set, that is when the working substance is placed on the source. So when this happens, the pressure changes, that is P1 changes to P2 by the time it reaches point B. Okay, so your P1 changes to P2. So this is pressure P1 changing to P2. Next is volume V1 changing to V2. As I told you, this process is a isothermal process. Isothermal expansion is taking place. So when this is the case, isothermal means the temperature in the system is kept constant. So it is just T1 which remains constant. Temperature remains constant. So whenever we conclude, whenever we take the integration part of the work done, that is work done is equal to integrating your pressure and change in the volume. We all know that PV is equal to nRT. This is the ideal gas equation, which is known as ideal gas equation. So when this is taken, you can take P is equal to nRT divided by V. What do we take? P is equal to nRT divided by V. And your nRT divided by V has to be substituted on equation star. Okay, so here we have W is equal to integral of n R and T is taken outside because this is constant, because we have for N mole of a gas, that is N, and R is nothing but the universal gas constant, and T is the temperature which is said to be constant under this process. So what do we have? Just 1 by V into dV. So always remember integration, you have the formulas. So integral of 1 by x or 1 by any number. So it is 1 by x is equal to log x. So that is the formula. So when that is the case, you can use W is equal to, you can write nRT, and integral of 1 by V is always log x. So it can be written as log V. I'll write it as log V, okay. So, and the volume, from where to where the volume is changing. So, it is from V1 to V2. So, I can write this as from V1 to V2. So, that is the one which is varying. V is a volume which is varying. So, here we are taking V1 to V2. There is no presence of pressure in this equation. So, we are considering volume changes there. So, here nRT log V, V1 to V2. How can you rewrite this? How can you simplify this integrated equation? It can be written as W is equal to nRT log V2 minus log V1. Again, it can be simplified as W is equal to nRT log V2 divided by V1. So this is how you write the work done for the first set. So it can be called as equation 1. Under equation 1, the curve, whatever it is represented, is said to be AB, that is the isothermal expansion. And during isothermal expansion, what is the work done? That is W is equal to nRT log V2 by V1. This is for N mole of a gas because N is present over here. So W will be W1 because this is the first set of equation wherein I told you we have got 4 steps in this Carnot cycle, out of which this is one step of Carnot cycle. So we have W1 is equal to N is for N mole of a gas, R is universal gas constant, and T, this is T1, just because everywhere it should be T1, just because we are dealing with T1 set of temperature. The temperature is not changing. It remains constant throughout this curve. So T1 log V2 by V1. So this will be the representation of isothermal expansion which comes along the curve AB. Okay, so let us move to the second set, that is representation of curve BC. Okay, so here we have got the PV diagram. This was our AB. This will be our BC. The complete solid line, whichever I have drawn here, we are working on that line, okay? The rest of the dotted lines are the previously done graphical representations, okay? So it's not necessary for each and every step you have to give this graphical representation. You can give an overall graphical representation either at the beginning or at the final. Usually we'll give it in the beginning, okay? So this here we are representing the curve B and C. So what happens in the curve B and C? So here the pressure decreases even more, whereas the volume starts increasing. So this is the pressure wherein the pressure is decreasing, it is coming downwards, but the volume is increasing. It has got a slight deviation. That means the volume is increasing. Okay, so here what happens to the working substance? The working substance is placed on the insulating stand. So there is insulating stand. At this condition, adiabatic process takes place. Okay, so what is meant by adiabatic process? So adiabatic process means there is no exchange of temperature between internal working substance as well as the external atmospheric conditions. Okay, so that is the temperature changes, but there is no exchange to its surroundings. Therefore, the adiabatic expansion is the one which takes place here. So, it can be written as adiabatic expansion. So, here isothermal expansion got over. Next was adiabatic expansion. So, what do we have? When the working substance is placed on insulating, which is also called as non-conducting. Non-conducting means the one which doesn't conduct. And what is that? The one which doesn't conduct, that is insulators. So here we have placed on insulating or non-conducting stand. What happens when this is the case? So our pressure was in P2 condition and volume was in V2 condition, but T, the temperature from here to here, it was remained the same, that it was T1. So it was in T1 condition. So my pressure also changes, volume also changes, temperature also changes under adiabatic condition. Now the temperature is not constant because it's not undergoing isothermal, but it is undergoing adiabatic process. So your P2 changes to P3, V2 changes to V3 and T1 changes to T2. So you have P3, V3 and T2. Never get confused with the temperature, how it goes on. Okay. So when this is the condition, we have according to adiabatic process, we have PV gamma is equal to K is the formula. So, P is equal to K divided by V gamma will be present over here. So, when you just consider for the work done W is equal to integral P into dV. Okay, that is the equation. So, integral from what to what? In a previous representation, we had taken from volume V1 to V2 because volume changes from V1 to V2. Now, we are supposed to take V2 to V3. So, it is like V2 to V3. So, when you just equate this, you will have W is equal to integral of K is taken constant because since it is constant, it is taken out. Integral V2, V3, 1 by V gamma into dV. So this 1 by V gamma can also be taken as, let me take this V gamma to the numerator. Okay, so it becomes W is equal to K V2 V3 V minus gamma into dV. So this set of equation can be written as, like you have got a formula, V minus gamma can be written as, that is x to the power of n can be written as V minus gamma plus 1 divided by minus gamma plus 1. So this is of the form x to the power of n is equal to x to the power of n plus 1 divided by n plus 1. For this power you have added plus 1 and you have taken this powers to the denominator. That is how you write the equation for the integration when it is like x to the power of n form in integration. So this is like x to the power of n. So it is x to the power of n plus 1 divided by n plus 1. So I can write it as W is equal to K, and when you're writing the formula of this integration, it's not necessary that you have to take this sign again. So you're just writing the formula integration of x to the power of n, that is integration of V to the power of minus gamma can be written as V minus gamma plus 1 divided by minus gamma plus 1. So you have V2 to V3. From down to up we are calculating. From where to where? When it is like from where to where, we are giving it from down to up. Initial condition to the final condition. But when we are simplifying the integration part, what we will get? We will have to take from head to toe method. Okay, so now it is W is equal to, done with the initial to final condition, but now our work is to take from head to toe method. So it is K into minus gamma plus 1. I'll take this as common out, so that I'll just write 1 minus gamma. Okay, so we have V3 minus gamma plus 1 minus V2 minus gamma plus 1. So this is how I write the equation. After this equation, we have got W is equal to K. Let us multiply K with V3 and K with V2. So we have K V3 minus gamma plus 1 minus K V2 minus gamma plus 1. So your 1 by 1 minus gamma remains outside. Okay, so W is equal to 1 by 1 minus gamma. K into V3 is nothing but your PV. You can, so it is K into V3 minus gamma can be written as this minus gamma goes down, so it becomes K divided by V3 gamma, V3 to the power of gamma, which is of this equation. So I can write your P over here. So I can write this equation as P3 V3 gamma into V3 gamma plus 1 minus gamma plus 1 and minus P2 V2 gamma and V2 minus gamma plus 1. So your power of gamma and minus gamma goes. So it becomes W is equal to 1 minus 1 minus gamma into P3 V3 minus P2 V2. So this is the equation what we have. So what is this PV? PV is nothing but nRT according to ideal gas equation. So this PV becomes W is equal to 1 by 1 minus gamma into nRT2 minus nRT1. Why this is T2? T2 because during the third condition, the T2 remains as it is. That is T1 changes to T2. But in the first condition, that is when the pressure changes from P1 to P2 and V1 to V2, the temperature remains T1 itself. So I told you don't ever get confused with the temperatures. So what this becomes? We have this overall equation as W is equal to, we have nR gamma minus 1 and we have T1 minus, so T2. So this is all about your working condition and it can be given as equation 2 and this is W2, that is second work done by the working substance when it is placed on the insulators, that is insulating stand or a non-conducting stand. So that is all about the representation of curve BC, which is known as adiabatic expansion. Now let us move to the next curve. So we have got our PV diagram. So it is known as PV diagram. So now we are representing curve CD. So curve AB got over, curve BC got over. Now it is curve C and D. So it is of this, the arrow mark shows towards left hand side. Okay, so now what process undertakes here? It is nothing but the isothermal compression. So till now it was just the expansion, now it is compressing. Okay, isothermal compression was the one which takes place. So what happens to the working substance here? The working substance is placed on the sink at this position. So when the working substance is placed on sink, so the pressure P3, volume V3 and temperature T2. The pressure P3 changes to P4, V3 changes to V4. But what happens to the temperature during isothermal compression? It remains constant. So I can write this as it remains constant. So when this is a case, what happens to the work done can be written as W3 is equal to integral P into dV. So here the volume changes from V3 to V4. So I can write this as V3 to V4. Okay. So P we have According to ideal gas equation, we have PV is equal to nRT. Okay, the same process is taken to here, that is W3 is equal to the working substance we consider here is the ideal gas. That is why we just consider ideal gas equations. So nRT into dV, nRT into dV divided by V. So nRT will be your constant terms. So here we are lying with T2. So W3 is equal to nRT2 integral of V3 to V4, and here we have 1 by V into dV. So this equation is like same as that of the first equation whatever we have worked out. So it is like W3 is equal to nRT, and we have 1 by V into dV. Integral of 1 by x is nothing but log x. So in the place of x we have V. So I can write it as log V from V3 to V4. Okay. So W3 is equal to nRT log V4 minus V3, that is head to tail method. I have equated V4 and log V3. Next we have W3 is equal to nRT log V4 divided by V3. So this is T is nothing but T2. Where there is T, you have to represent in T2. So we can write this equation as W3 is equal to nRT2 log V4 by V3 can be interchanged to V3 by V4. Okay. So it is like from V3 it is going to V4. So it can be written as log V3 by V4. When you just interchange it, what happens to the sign? It becomes negative. So this is the equation known as equation 3, and this is the representation of the curve C and D. So we have work done. W1 we got, W2 we got, and W3 we have got. Next will be the W4, that is the fourth work done. I told you there are 4 steps. So lastly, we are going to the fourth step. So what exactly is in this fourth step? Representation of the curve dA. So we have got pressure and volume here. So this will be A, this is BC, so it is AB, and this is C, and again this will be in dotted lines, so it is known as D, and we have D and A. This is the last set of equation wherein this is considered to be adiabatic compression. So first of all we had isothermal expansion, adiabatic expansion, next it is getting back, so it is isothermal compression, now it is adiabatic compression. Okay, so the vertical graphs are always adiabatic conditions, horizontal curves are always isothermal conditions. One is expansion, one is compression, that's all is the difference. So here when the working substance is placed, when the working substance, when it is placed on the insulating stand, what happens during this condition? That is, we have, according to adiabatic condition, we have P V gamma is equal to K. So P is equal to K divided by V gamma. Okay, this process is the same as that when you keep the working substance on the insulating stand. Same way here also the working substance is kept on the insulating stand. How there you get adiabatic expansion. Similarly, now you get adiabatic compression in this case. So here we have pressure P4 and volume will be in V4 and temperature will be in T2. So P4 changes to P1 because it's a cyclic process. It's coming to its initial position again. So it is P1. V4 changes to V1 and T2 changes to T1. So we have the initial condition P1, V1 and T1. This is the initial condition. So again when you solve, W is equal to integral of P into dV, where your volume changes from V4 to V1. We end up with the equation, since it is work done, the fourth work done, we end up with the equation. Without solving, I'm just directly writing the equation because it's the same process as that of the second step as you have done in this. That is representation of curve BC. So we have W2 is equal to NR divided by gamma minus 1 T1 minus T2. Okay, so here I can write it as W4 is equal to NR divided by gamma minus 1. Here we will end up with, we have T1 and T2. So it is now T2 to T1 back again. So the equation becomes NR divided by gamma minus 1 and T1 minus T2. You will have this set of equation known as equation 4. Okay, so we have equation 1, 2, 3 and 4. When you have this equation, so next what are you supposed to do? So we have the overall graph. How is the overall graphical representation? I'll just give it here. So the overall graphical representation can be given as P and P diagram. So we have A, B curve, C curve, D curve and back again. So the arrow marks is must and should for you to follow the path. So this will be isothermal expansion and this is adiabatic expansion, and here CD curve is isothermal compression and DA curve is adiabatic compression. Okay, so this is the area under this curve is said to be the work done. So this is the work done. It's not necessary that you have to draw this lines. It is just that you have to follow the curves. Okay, so now in order to calculate efficiency, we use the formula eta is equal to, what is the efficiency you have? 1 minus Q2 divided by Q1. Okay, so as we all know, when the working substance is there, W1, you will just fuse all the working substance together. You will add up the working substance as W is equal to the total working substance, W1. So let it be in a big letter, W2 plus W3 plus W4. This will be our W1, wherein nRT1 log V2 by V1 and W2 is nR divided by gamma minus 1 T1 minus T2 and W3 is nRT2 log V4 by V3. So it can be written as V3 is equal to minus nRT2 log V3 by V4, and lastly we have W4 is equal to NR divided by gamma minus 1 T1 and T2. So the second one as well as the fourth one both are same. So what happens? But with a negative sign. So it is same but with the negative sign cancels each other. So we remain with capital letter W is equal to W1 plus W3. So what is that W1 and W3? It is nothing but RT log V by V. So it is V2 by V1. At that time the temperature T will be T1 because we have plus here and the equation consists of minus, so it becomes minus RT, and last equation will be minus nRT2 log V3 by V4. So minus RT2 log V3 by V4. Okay, so N will be for N moles of a gas, which we don't consider here. So it will be RT, T1 and T2 conditions over here. So it is W. So when you have this efficiency equation, you have to convert this heat supplied to temperatures. Okay, so when that is the case, what are the things you have to consider? It is nothing but from equation 3 and 1, that is this equation and this equation, when we can just write it as the heat supplied Q2 divided by Q1, that is the heat supplied during second condition, that will be RT2 log V3 by V4. So what happens? This R and R gets cancelled, so what remains is T2 log V3 by V4, and we have the condition for Q1 given as T1 where R and R gets cancelled log V2 by V1. So we have this condition. We also know that under adiabatic conditions, how is the temperature and volume conditions given? So under adiabatic condition, adiabatic process, if you just consider the temperature and volume condition, that is TV, is given as TV gamma minus 1. So here we have TV gamma minus 1 is a general term which can be expressed as T1 V2 gamma minus 1 is equal to T2 V3 gamma minus 1. So this will be one set of equation. So let me consider this equation as equation 5 and this equation as equation 6. Again we have the same condition with the adiabatic compression. So it will be T1 V1 gamma minus 1 is equal to T2 V4 gamma minus 1. So this is the condition for adiabatic compression, that is during this process, D2A process. So let us consider this equation as equation 7. So equating equation 6 and 7, what happens, that is on dividing both the equation. So this equation divided by this means T1 gets cancelled with T1, T2 cancels with T2. So what remains is V2 gamma minus 1 divided by V1 gamma minus 1 is equal to V3 gamma minus 1 and V4 gamma minus 1. And finally what remains is V2 and V1, V3 divided by V4. Okay. So V2 by V1 and V3 by V4 can be equated in this position. So that is V3 by V4 is same as that of V2 by V1. So I can equate for this. So when I equate for this equation 5, what is my equation? So it stays like Q2 divided by Q1 we have, which is equal to, we have T2 log V3 by V4 we had, and again T1 log V2 by V1 was the equation. Now the case is Q2 by Q1 is equal to T2 divided by T1 log, and we have log. So here V2 by V1, V3 by V4 is substituted as V2 by V1 according to the last simplification. This cancels with this. So what remains is Q2 by Q1 is equal to T2 by T1. So now overall, therefore, the efficiency can be written as 1 minus Q2 by Q1 can be written as T2 divided by T1. This is the temperature condition of the efficiency. So this is the end of the Carnot cycle. So I hope the Carnot cycle is not that tough as you think. It is just that you have to understand what happens when the working substance is placed on a source, insulating stand, sink, again back to insulating stand. There are two processes which multiplies later, that is isothermal compression, isothermal expansion, adiabatic compression, adiabatic expansion. So two process. Under two process, it again undergoes two other process, that is compression and expansion, compression and expansion. It is played only with the isothermal conditions and adiabatic conditions, and finally we end up with the efficiency. So here ends our topic, that is thermodynamics chapter with this Carnot cycle, and it is very important on the exam point of view, which comes for the 5 marks. You will have to explain. It's not necessary that you have to do all the integration process what I have done. It is just for you to understand how the formula is obtained. Okay. So you can just explain when the source is kept, where, and what happens to the pressure, temperature and volume, and then you can just give the final expression, and along with that you will have to, must and should, you will have to draw the graphical representation. So you have to explain each condition. There is nothing that you have to derive or you have to do the mathematical expression. It is just that explain 4 steps with the graph. So 5 marks will be in your pocket. So that's all you have to do. Here I have elaborated a little for you to understand. That's all. Here ends our thermodynamics chapter. Let us all meet in our next chapter. Until then, have a good day. Thank you.